Good afternoon, everyone, and welcome to today's webinar on why your vacuum technology choice matters. My name is Megan Parrish, and I'm the Senior Editor for Pharma Manufacturing Magazine, which is producing today's event. Today's event is sponsored by Bush Vacuum Solutions. Today we're going to talk about how to choose the right vacuum technology. It may sound simple, but there's no single ideal solution for all pharmaceutical applications. So when going through this process, all of the parameters need to be carefully considered in order to derive optimal solution. Vacuum technologies have also been continuously evolving for the past 2 decades, so it might be a good time to reevaluate your options. For example, replacing traditional liquid ring vacuum pumps with dry screw technologies can reduce energy, increase reliability and performance, and benefit the environment, as well as save you money. So here's what our speakers are going to cover today: vacuum basics and technologies, understanding pharmaceutical process considerations, choosing the optimal solution, and total cost of ownership. To complement this discussion, we will have a live audience-driven Q&A session at the end of the presentation, so please submit your questions as they occur to you. Now, before I introduce our speakers, there are a few housekeeping issues that I need to review. On your screen, you should have 4 primary sections. The upper left or audio section allows you to adjust the volume. Just hover over this section until you see the audio volume control to adjust it. Below that is the Ask a Question box. At any time during today's presentation, you can type your question for our presenters right here, and we'll get to your question during the Q&A. And if you're having technical issues, you can simply type in your question or concern in the Q&A box, and one of our technical engineers will help. Underneath the Ask a Question box is our handouts area. Here you'll find additional information available for download. Then, in the largest section, you'll see today's presentation slides. And below the slides, you will see a live chat box. Here, the chat box is a little different. In this box, you can chat with your fellow webinar attendees or presenters. But if you have a question that you want answered in the Q&A section, please don't put the questions in this area because we won't look for it here. Now, if you need a better view, enlarge a section by clicking on the box in the top right corner of the section next to the X. If you accidentally close out a section, don't panic. You can get back to it by clicking the refresh button at the bottom of the screen. It's located to the left of the icons. Also, this webcast will be archived. We encourage you to direct coworkers to the recorded presentation. It'll be available on the Pharma Manufacturing website. We've also recently added a Q&A feature to our on-demand presentation so that listeners can ask the speaker a question and then it will be passed along to them. And one final note, we ask you to respond to the feedback form at the end of this presentation. Your answers will help us improve future events. So with that, I'm going to introduce our speakers. Today we have Teodora Kuzmina, who is a product marketing manager for dry claw and dry screw vacuum technology at Bush. She also has previous experience working with vacuum applications in the medical industry. Teodora received a bachelor's in biomedical engineering and master's in process engineering from Babeș-Bolyai University in Romania. Today we also have Michael Sciulino, who is a systems engineer for Bush and works within the applications team, primarily focused on chemical and pharmaceutical applications. He has previously worked for Waste Rock and Innovation as a scientist and engineer. He got his bachelor's from Kent State and master's in mechanical and nuclear engineering from Virginia Commonwealth University. So with that, I will hand the floor over to Teodora and Michael.
Well, thank you, Megan. And hello, everyone. My name is Teodora Kuzmina. Thank you for taking your time to join our webinar today. Today, we will be talking about why your vacuum technology choice matters. I hope everyone is doing well and staying healthy, practicing social distancing through these difficult times. We're really excited, though, to be here today and discuss about vacuum solutions. Our plan is to go over the importance of choosing the right vacuum technology, all dependent on your application. We will start discussing first about what is vacuum, browse through different vacuum technologies, and we'll focus on liquid ring and dry screw technology. Then Michael will be taken over and focus on what we consider important in the pharmaceutical industry. We will look over a case study and the total cost of ownership, advantages and disadvantages, and conclude with why it is important to consult with a vacuum expert, as well as a Q&A session. First, what is vacuum? As a definition, vacuum is a space devoid of all air or gas. We generate vacuum when we remove molecules from a fixed volume. The term of operating under vacuum is used to describe a process where the pressure in the system is less than the ambient atmospheric pressure. Vacuum is the opposite of pressure. So when you have high vacuum, that means you have low pressure. Also, there are several units of measurement to describe the level of vacuum. Vacuum can be measured in torr, inches of mercury, inches of water, millibar, but there are also different regions of vacuum, from rough vacuum, which is from 760 down to 1 torr, mainly used in applications like packaging or processing. Medium vacuum, which is from 1 torr down to 10 to the minus 3 torr, which is semiconductor, freeze drying. And then we move into the high vacuum, which is 10 to the minus 3 to 10 to the minus 7, mainly coating, metallurgy, laboratories. And anything below 10 to the minus 7, we consider ultra-high vac, which is thin films, research. Medium to rough vacuum range is typically the pressure we operate at in pharmaceutical applications. Now, vacuum can be expressed in either gauge or atmospheric values. Now, there's a simple rule of thumb here. Gauge values start at 0, while absolute values end at 0. Another thing to keep in mind is that the pressure changes with altitude. Ambient pressure here in Virginia Beach, it's about 14.7 psi, about 29.9 inches of mercury, while in Denver, at over 5,000 feet, ambient pressure is around 12 psi. You lose about 25 torr, about 1 inch of mercury with every 1,000 feet. So be mindful of using gauge values at altitude when talking to vacuum experts. In vacuum, because we handle a lot of gases, we use the ideal gas law, which describes the physics between pressure, temperature, and volume. The law is a generalization containing both Boyle's law, pressure law, and Charles' law, which are basically inverse relationships of each other. The law states that the equation of state of n gram moles of a perfect gas can be written as PV equals nRT, in which R is the universal gas constant. We use this equation to calculate mass flow and volume flow of the gas that we will be pumping. Now, vacuum is used all over the world in many, many industries, from food to offshore oil and gas to chemical and pharmaceutical. In this presentation, we will focus on the vacuum technology on the pharmaceutical market. Pharmaceutical market relies on vacuum technologies to meet safety standards and stringent quality demands by a highly regulated market. Vacuum technologies have continued to develop over the past few decades. Customers are looking for a complete, a safe, and a reliable solution. Nowadays, multiple technologies allow us to find the most appropriate solution that best fit any application. The most common technologies used in the pharmaceutical markets are from dry screw vacuum pump, a liquid ring vacuum pump. We also use one through oil-sealed rotary vane, which is a sealing pump where fresh lubricant is continuously injected to lubricate veins. This technology is very forgiving due to the protective oil coating on the vapor contacting surfaces. However, the oil spent for the vacuum pump is considered hazardous waste and must be treated accordingly. Now, we also use boosters in the pharmaceutical applications. Together with the vacuum pump, you can achieve higher pumping speeds and lower ultimate pressures. Today, we will only focus on the first two technologies, the dry screw and the liquid ring vacuum pump. Bush has the benefit of offering multiple technologies and can find the best fit for any application. Often, pharmaceutical applications give the vacuum choice between liquid ring and dry screw pump, which we will be comparing today. Looking at the vacuum scale, they both fall into the rough to medium regions. Now we're going to be moving into talking about the liquid ring vacuum technology. This is a well-established technology and is being used in many, many applications. The principle behind the liquid ring was developed in 1890s as a water ring pump. Over many years, the vacuum pumps have proven themselves to be robust, reliable vacuum generators and chemical processes. Looking at the operating principle an eccentrically mounted impeller rotates within the cylindrical housing. The housing is filled with the operating fluid to the extent that the vanes of the impeller are immersed in the fluid. The operating fluid can be from water to any liquid compatible with your gas or vapor to be evacuated. The rotary motion of the impeller can, and the resulting centrifugal force cause the liquid in the housing to form the so-called liquid ring. The gas travels between the impeller blades and is compressed by the liquid ring. The liquid ring seals the individual spaces down to the cylinder. Therefore, it is sometimes referred to as the sealing fluid instead of the operating fluid. The liquid ring seals the gas chambers, cools the incoming gas, absorbs the heat of the compression and the compression from the condensation, removes impurities, cools and lubricates the sap shield. These pumps are ideal for wet and corrosive processes. The pump size ranges from 25 up to almost 27,000 cubic meter per hour with an ultimate pressure of 25 torr. Due to the operating fluid used, the mechanism can only be used in the rough vacuum range. The reason for this is that the achievable vacuum levels depend on the vapor pressure of the operating fluid, which is constantly pumped through the vacuum pump. This allows the liquid ring vacuum pump to be operated at relatively low temperatures. And in addition, the temperature rises of the medium is kept to a minimum during the compression phase. For these pumps, packing and as well as a variety of mechanical seals are available, including API 682. Now we're going to be moving into talking about the dry screw vacuum pump. This is widely used in the chemical and pharmaceutical industry. This technology, though, is relatively new to the market compared to other industries and is gaining more and more popularity in many industries and applications. It was launched in the 1990s due to the clean process requirements initiated the development of this pump. The main advantage is that it does not require operating fluid to compress the process gas. When looking at the pump principle, in the screw vacuum pump, there are two screw-shaped rotors which rotate in opposite directions. The gas is trapped between the cylinder and the screw chamber, compressed and transported to the gas outlet. The screw rotors do not come in touch with each other or with the cylinder. There are small clearances between the screw and the housing, which assure the sealing without lubricant, guaranteeing a low ultimate pressure. The dry screw is a single-stage twin screw vacuum pump. The cooling jacket ensures even temperature distribution and greater thermal efficiency and stability throughout the pump body. The modern screw pumps have variable pitch screw, which result in even compression of the gas across the entire length of the screw. There are many advantages here, from ensuring same temperature distribution that can be easily monitored and controlled to low power consumption from energy and cooling water savings, as low as low gas temperature. There's no compression against the end plate, eliminating the possibility of hot spots. The dry screw has several seal options. Labyrinth or mechanical seal selected by the application engineers when analyzing your process gas chemical composition. In addition to the seal purge gas, flow option can be added to help and protect the mechanical seals and gearbox from contamination. The seal barrier purge is basically the injection of nitrogen gas into the seal, and by creating overpressure here, you keep the process gas out of the gearbox. So the main advantage here is protecting your gears, the bearing, and any type of oil contamination. The beauty of these pumps is that they can be designed for nearly all process gases thanks to the seal material and coating selection, as well as temperature regulation. There are many things to consider when selecting the right vacuum pump for your application. We constantly look and compare the challenges in order to find the best solution. Now, comparing the two technologies side by side, we see that the liquid ring vacuum pump has a much deeper capacity, while the dry screw can achieve much deeper vacuum. The liquid ring requires an operating fluid, while the dry screw, you have dry compression, no contamination reaction possible between the process gas and operating fluid. Now, the initial investment of the dry vacuum pump is often higher than the equivalent in a wet pump, but there tends to be a little difference when the total installation cost is considered. When running costs taken into account, the dry system often shows a considerably lower cost of ownership, and we will show you this later in our case study. It really also depends on the material of construction, because if we're talking of exotic materials with liquid rings, we will see the prices jump up significantly. Speaking of material of construction, the beauty of the liquid ring is that you have a variety of options for material of construction, which are carefully selected, again, depending on the process, from cast iron to stainless steel, all the way to titanium. On the dry screw side, due to the lack of condensation, the pump can be fabricated from inexpensive cast iron. Now, the ductile iron is the material used for the process wetted parts that contact the pumped medium. Also, coatings are available for additional protection. By knowing the composition of the process gas, vacuum experts can carefully select the coating to be compatible with any chemical. A xylene coat is mostly used for application with water vapors and non-corrosive chemicals. And Tentol is a nickel plating, which is resistant to any chemicals with very few exceptions. Corrosion. Now, when we talk about corrosion, the corrosion of the pump internals is a threat for any vacuum pump, leading to from loss of performance to pumping speed decreases. The ultimate pressure of the pump rises, as well as power consumption, eventually leading to the pump or process failure, which can be very costly, especially in pharmaceutical industries. In order to avoid corrosion, we take a look at the material of constructions again. The high variety of materials of constructions in the liquid ring, like stainless steel option, prevent corrosion in the pump. Also, the low temperatures in the pump are favorable for condensing of process vapors. To an extent, this means that a vacuum pump additionally functions as a condenser, and because condensation takes place, then the mixture enters the vacuum pump, the volume is drastically reduced. In addition to the condensing effect, this also achieves an increase in a nominal pumping speed. So be mindful here not to cavitate the pump with too much vacuum or too hot water. Here's where solvent recovery options are available. A liquid ring pump should be kept with liquid inside, about half full. They're typically installed at the lowest point of the system to allow all fluids to flow in by gravity, excess being removed through a separator. A screw pump should be kept dry. They should be installed at the highest point of the system. Reason, to prevent liquid from flowing back into the pump after the shutdown. The high discharge temperature in a dry screw pump allow pumping speeds of high corrosive vapors, as they do not condense inside the compression chamber. There should be no liquid into the dry pump. The gas ballast valving option also helps prevent process from condensing inside the pump. Now, how do we prevent condensation? For the liquid ring, be mindful of the chemical compatibility of the service liquid and the material of construction. For the dry screw, the list is a bit longer, but first you have to check compatibility with the material of construction, select the appropriate coating, condense any corrosive vapors before the pump, maybe by using a pre-condenser. Warm the pump before the process starts, I would say for about 30 minutes. Run the pump pump hot to avoid condensation. And when I say that, I mean check the boiling temperatures of the gases. Make sure they're all kept in that vapor phase. Flush the pump with solvents or inert gas after the process. Assure there's no backflow into the pump when it's turned off. And last but not least, assure that condensates drain off pump exhaust continuously. For the dry screw, depending on your process, we might recommend flushing. In flushing process, we're basically injecting a liquid at the pump inlet that has the objective to clean the pump in order to avoid any blocking between process or during standstill. Automatic flushing with suitable solvent is done at regular intervals to make the system maintenance-free, hence added value into the system. In most applications, it is recommended to warm the pump up prior to the process operation and purge the pump with an inert non-condensable gas. Typically, we're talking about nitrogen here, to remove the process vapor and any residual liquids prior to the shutdown. We typically recommend flush functions to be installed in conjunction with the purge to ensure that the vacuum chamber is free of any process contaminants. If the purge function is not utilized, the control panel is equipped with a minimum run timer to limit the amount of starts per hour. In the dry screw pump, we use the cooling water to pass through the cooling jacket and only in contact with the exterior heat exchanger. In this case, no water contamination occurs, which makes the process economical and keeps the environment clean. In some cases, we can also offer options for radiator-cooled pumps to eliminate any kind of water. On the opposite side, the liquid ring does require chilled water source as well as fluid disposal that can be very costly. For the liquid ring vacuum pumps, it is possible to have a partial or full water recovery system for both the vacuum pumps, sealing water, and cooling water. The continuous flow, also known as once-through liquid system, the discharge mixture of gas is separated. The used service liquid sent away to waste or for remote treatment. It is not the most efficient, it is costly, and not environmentally friendly. Partial recirculation liquid system reduces the volume of fresh liquid consumed. A portion of the used liquid is mixed with fresh liquid to help maintain constant temperature and reduce the operating costs up to about 50%. The closed fluid circulation, also named as total recirculation, is the most efficient system. It separates the service fluid from the cooling liquid. Now, possible contamination of the operating fluid with condensate from the process gas affecting performance, and which making it necessary to treat the operating fluids before its disposal. So again, it can be very costly. The sealants must be selected to match the process vapors condensing in the ring. Gas solubility must be verified if it exists with the ring composition. Another thing to watch here is the temperature. As you can see in the graph, a portion of the pumping chamber in the liquid ring vacuum pump is occupied by vapor that is evaporating from the service liquid. The cooler the service liquid is, the less evaporation will take place and greater suction will be obtained. Due to the tight internal clearances in the dry screw pump, possible damage can be created eventually to lock the pump up. And now, as you can see, the pump cannot tolerate condensing and slug due to the tight clearances, and which will result in reliability issues. Liquid ring is more robust. The tolerances are much higher, allowing condensing and slug to pass through. The liquid ring efficiency increases with condensing. As I mentioned before, the liquid ring is a natural condenser. The liquid ring vacuum pumps can handle a large amount of liquids and the dirtiest processes, having high tolerances for harsh environments. Even though some customers are hesitant here due to the tight clearances with a dry screw, there are many solutions like KOPs or filter systems that can be added and for preventing particles from entering the pump. They can become costly though. Another important category when selecting the vacuum pump is the energy efficiency. The dry screw pump has some advantages here, with less energy needed, less power needed, a slow run at 20 hertz in comparison with the liquid ring vacuum pump that needs a minimal speed of 35 hertz to maintain the liquid ring. Shorter process cycle with a dry screw due to the constant vacuum level through the system is an advantage as well. In terms of energy efficiency, the dry screw tends to be about 30% more efficient. On a maintenance side, the dry screw pumps require exchange of lubricant in the gear chamber, and because of the tight clearances, inlet filtration system must be maintained. There's simple maintenance schedules in both cases. Overhauls are complex and can be expensive due to the on the dry screw pumps due to the screw recoating, which is necessary. The liquid ring vacuum pumps are easy to maintain and rebuild. The mean time between failures is less on the liquid ring vacuum pump. Now, I would like to thank you for now, as I'm going to turn the presentation over to Michael, who will be continuing on with applications in the pharmaceutical industry.
Thank you, Theodora, for that informative presentation. I hope everyone's staying healthy and safe out there during these difficult times. Good afternoon. My name is Michael Sciolino, and I'm going to be continuing to discuss the pharmaceutical vacuum industry, and in particular, how to choose the right technology for the various applications. The pharmaceutical industry presents its own set of challenges and requirements that must be understood. Of course, at the forefront, we have to deliver a solution that does what it needs to do, and that includes having the right pressure and having the right capacity requirements. Essentially, we have to make sure it works. Beyond that, there are other considerations such as maintenance, integration, efficiency, and other means that you want to take in consideration. I like to compare the pharmaceutical vacuum industry like the aircraft industry. So unlike a car, you can't pull over an airplane on the side of the road if you have an engine failure or some kind of mechanical failure. Therefore, you have to have these backup and safety features in place, and the same is going to be true for the pharmaceutical industry. Now, I really want to emphasize that reliability and safety are paramount. Therefore, high-end, reliable, and accurate instrumentation need to be used. The chemicals in a single batch could have a worth of over hundreds of thousands of dollars, and all that would actually be destroyed if we lose vacuum for a period of time. Serviceability is also really important, and we do this to ensure that we minimize the downtime of the systems. And in the case there's a failure of any reason, we want to make sure that we have another option in place. Bush has strategically placed service centers that we have around the world, as well as trade and service replacement policies for exactly this reason. Here you see listed some of the many pharmaceutical applications that utilize vacuum, and of these we're going to touch on a few briefly. Many of these applications use reactors, in which case the vacuum is sometimes used to speed up the reaction and does this by removing byproducts. It can also perform chemical transfer, and sometimes it aids in the evaporation of solvents. Now, in the case of using the solvents, it's sometimes good to have a post-condenser, and that's particularly if you have a dry screw pump, and that's so you can collect the solvents at the end. Or if you use a liquid ring, sometimes you can actually use the solvent itself as a sealant. Dryers are also common, and they might be something like a Nooch dryer, or sometimes we have drums or even small-scale tray dryers. Now here again, both technologies can be used, but it's really important to ensure that the chemicals being dried don't condense in the pump, and that's if you're using a dry screw. Distillation is the process of separating a mixture of soluble liquids by taking advantage of the difference in boiling points or the vapor pressures. And when you do that, it generates a different composition than what you started with, and this is also common. Here, the dry screw pump is often useful in these chemicals, particularly when they have low boiling points or relatively low pressures. And lab systems are also common, and typically with the lab systems, you're going to be using a central vacuum system. And with any central vacuum system, you might have a combination of chemicals and a variation of chemicals that are being pumped. Therefore, when dry screw pumps are often used because they're generally a little bit more versatile compatibility-wise. While working with the vacuum experts, there are several important inputs which must be known in order to have a proper design. Now, the general inputs are listed here, but there's going to be a few that for any system the designer needs to know in order to properly design it. These systems are required. These systems include the required pressure and how to control it, whether you're using a VFD, a control valve, or some other means. We also need to know the temperature, and knowing that in conjunction with the pressure tells you what state the chemicals are going to be in. We also need to know the capacity to properly size the system, and of course the chemical composition itself. Now, it's important to realize that in the pharmaceutical industry, which is unlike other industries that utilize vacuum, it has a really wide variety of applications. It's also important to know that these companies are using it for different reasons and how to understand it. In summary, pharmaceutical companies create different chemicals for the use in production of pharmaceuticals. These can tell lots of chemical reactions, and some of which can create biohazardous byproducts or products. They generally have large production facilities, and a lot of times the vacuum system is only a small part of a much larger, more complicated, expensive machine. There's also a lot of research and development, and we have to take special considerations which include recoverability requirements, compatibility, and treatment costs. Now, that's why it's imperative that you speak with the vacuum experts who know these products and can apply them correctly. And this is especially true when we're working with the dry screw technologies, because these can be less forgiving and more expensive if they're not designed and used properly. Here we're going to take a look at an example system. We're starting off, we only know the inputs that are given and shown in the table. The first step is to convert the given capacity from SCFM, or standard cubic feet per minute, to ACFM. And we do that by using the ideal gas laws that Theodora discussed previously. Okay, to start off, we first adjust the pressure that's given in SCFM by multiplying by 760 torr, which is the atmospheric standard pressure, divided by our pressure that we're working at, which is 37.5 torr. We also adjust for the temperature by multiplying by 303 Kelvin, which is the temperature in Kelvin that we're given, divided by the atmospheric pressure in Kelvin. Now that gives us 235 ACFM. Now in reality, we're likely to see a mixture of chemicals, and we need to account for all those and know the actual molecular mass ratios. But for simplicity of this example, let's just assume it's the one chemical. Now, if you look at the second equation, we're given the mass flow of methanol, and this can be converted to a flow rate by again applying the ideal gas laws. This works because we're applying Avogadro's number, and that tells us that the number of units in 1 mole of any substance is constant. And we already know the mass which is given, the temperature and pressure all given, and we can look up the molecular weight of methanol. That gives us about 34 cubic meters per hour, and we can convert that to 27 actual cubic feet per minute. And I'll just tell you that massive unit somehow works itself out. Subtracting from the total flow of 235 actual cubic feet per minute, we get a flow rate of 208 ACFM, and that's of air. And working backwards, we can actually calculate the mass flow there, and that's used in the sizing calculations. Now, we must understand the properties of the chemicals in order to design the best solution. Now, in this case, we only need to consider methanol. And if you notice, it's relatively volatile. You can see that through the vapor pressure curve that's given on the right side of the screen. It's also miscible in water, meaning that's soluble. And in water, it's going to form a homogeneous solution. Therefore, we can actually dismiss the full recovery liquid ring vacuum pump system as an option, because with the methanol, it's going to mix with the water, and it's going to make that substance and make the seal fluid much more volatile. Now, by doing so, that's going to reduce the vacuum capacity. It changes the ultimate vacuum, and that's going to keep increasing as the amount of methanol increases in seal fluid. So our two options here are either to use a once-through liquid ring system, or we can use a single-stage dry pump. Now here you see a simplified version of the P&ID for a dry solution. Now this is omitting the electrical controls. The system here is fitted with a nitrogen purge, and you can see the components that are used to dry the contaminants out. You notice the standard temperature switches, and we also have that on the cooling water and exhaust. The process has an isolation valve as well as a nitrogen inlet to allow for the purge sequence, and that's going to be necessary in this case to make sure that the pump's dry after shutdown. You also notice devices such as flow and pressure regulators on the seal purge. That's used with the nitrogen in order to control what's going on for the seal. On the right-hand side of the screen here, we see a once-through liquid ring vacuum pump system. So the system includes a liquid ring motor and pump, and you also see a separator as well as control mechanism to control the fresh fluid seal. Now, almost every kind of liquid ring pump is going to need a separator, whether that's a once-through partial recirculation or total recirculation, to separate the liquid from the gas, and that's true for any system. Now, if it's a full recovery system, you'd also need a heat exchanger, and sometimes those also require a recirculating pump. Here we're comparing the total life cycle cost of ownership, and we do this using the calculated capacity requirements from the last example, and we size it for both of the systems. These are the prices for the basic accessories seen on the previous P&IDs, and we omitted the electrical control. You can see that the initial investment for the dry screw is higher, but it requires less power. Now the energy shown is the actual calculated absorbed kilowatt power, and you can see the additional cost that adds up over time. The dry screw pump does utilize cooling water, but the once-through utilizes more. Now the dry screw pump does require a small amount of nitrogen for the discharge side seal, and that essentially trickles in at around 5 standard cubic feet per hour in this case. But that amount's relatively inexpensive compared to the cost of the rest of the system. The seal purge isn't a necessary option if you choose a lab seal version, but for most applications that involving chemicals and most applications in the pharmaceutical industry, we're going to have mechanical seals, which includes a necessary discharge side seal purge. As you can see, the dry screw investment in this case pays off after about year 2. You can see that in the chart on the right side of the screen. We also took into consideration 2 complete preventive maintenance overhauls, and that gives us a realistic picture of the total overall cost. Now here you can see the total savings, and that becomes more significant after the second year. If you remember, we selected a once-through system due to the methanol. Now, a full recovery would actually utilize more utility water in most cases. This is due to the additional requirement that we have a heat exchanger that also needs cooling water, even though the majority of the seal of water is actually recycled. Now here we summarize the advantages of the 2 technologies discussed in the previous application. Sometimes we have something that we actually haven't accounted for is the estimation and the fact that the customer would need to dispose of over 4 million plus gallons of the now contaminated water. And EPA regulations often charge companies taxes or you have penalties for disposal, and those can be pretty expensive depending on the chemicals that are being used. So we're going to take this as an advantage for the dry screw pump. The low energy costs are an advantage to the dry screw pump in this example, as we demonstrated through the case cycle. Now here we're giving the advantage to the liquid ring pump for the ability to have a wide range of casting materials. Because in this example, we had methanol, we're actually able to use the standard cast iron pump with a stainless steel impeller, and that helped us reduce costs. Here we see some of the various pharmaceutical applications mentioned, and the chart shows you the technology that's either well suited, which is denoted with a check mark, or if it's possibly suited for it, and we have a circle. You notice that the liquid ring pump is well suited for most of the applications. It's tried and true. It's been used in the pharmaceutical industry for many years, and we know that works. And you can see the dry screw pump is well suited for almost every application. But as we discussed, just because the solution works doesn't mean it's the best solution. and that's why it's important to work closely with the vacuum experts. Also wanted to mention that the once-through oil-sealed two-stage rotary type, it's also technology used in this industry. They're reliable and can be used for harsh or corrosive or sometimes even sticky applications. And that's because the sealing oil is pushed out along with the process. They tend to be reliable over the long term. They have their place in the pharmaceutical industry, but the high cost of the contaminated oil disposal usually makes the once-through oil-sealed rotary type only the best option when the other technologies will fail. Another technology that's used often in the pharmaceutical vacuum world are vacuum boosters. Now they work together with the vacuum pumps, as Theodora mentioned, and they do that to increase the capacity and ultimate pressure, and they can do that up to a factor of around 10. It works similar to a supercharger that you might see in your car. It works by compressing the gas and pushing it against the discharge seal. Now, if we remember what we learned from the ideal gas law, as the volume gets reduced and it gets squeezed together and the pressure is decreased, we're able to use much smaller vacuum pumps for the same capacity. This is especially useful in helping the liquid rings because the liquid ring can achieve the lower pressures, and we can achieve pressures that normally a liquid ring would start cavitating at. In conclusion, we discussed what vacuum means and how it's utilized in the pharmaceutical industry. We looked at liquid rings versus dry screw technologies. We discussed what's important to consider, specifically in the pharmaceutical industry, and what information is needed in order to deliver the best solution. We also looked at the case example and the total life cycle costs. All this was done with the goal to deliver the best solution, which will have reliable performance, that's cost effective, and can be incorporated in the customer's complete system. I want to thank you very much for your time. I'm now going to be handing the mic back over to Megan, and she'll be reading your questions. Thank you.
Okay, great. Thanks so much, Michael, and thanks so much, Theodora, for that thorough presentation. Just a reminder, everyone, if you have a question for our presenters, you can type that into the Ask a Question box that's on the left-hand side of your screen. We already have some questions coming in, so we're going to go ahead and dive into the Q&A section. I'm not sure, either Michael or Theodora, whichever one of you wants to go ahead and answer this question, feel free to jump in. The question is, why is cavitation a concern, and what does the cavitation valve on the liquid ring P and ID do?
Yeah, so I'll go ahead and take that one. So thanks for that. The cavitation has to do with when there's a high pressure differential for the liquid rings. What's actually happening is the oil, as you approach the vapor pressure, it actually starts to boil, and it creates these bubbles that are like near the surface area there, and those create like air pockets, and they quickly collapse, or essentially they implode back onto the metal, and that can cause damage. And it sounds like somebody's throwing like nails in a dryer. And having that anti-cavitation valve, what it actually is doing is you could either have one that's just open to the air, so it allows the pressure to be increased, or if you have a situation or a process that you can't introduce air into, we also can actually take the motive gas that's coming out of the discharge separator, recycle that back, and then use that to control the pressure as well.
Okay, great. Do you have another question? And again, whichever one of you wants to jump in on this. Why is there more water required for the full recovery system than the once-through liquid ring?
I can go ahead and take that one as well. So that's a good question, actually. So even though with the liquid ring that has the once-through system, it doesn't have a heat exchanger, and the heat exchanger is going to have to remove the same amount of BTUs essentially that the once-through would, but it's not going to be quite as efficient. So the general rule of thumb is actually that's going to use about 1.5 times the water you'd have with the once-through. But the big advantage though here is instead of having the liquid that's going to be contaminated on the discharge that you need to dispose of, it would just be going through a heating element, so you just have slightly warmed up water. But that's why it would actually have more that's required there.
Okay. And now we have a question about the case study that was referenced during the presentation. You referred to the maintenance on both technologies being low. Can one of you explain what is the maintenance schedule for the pumps that were referenced in the case study?
Okay, I guess I'll jump and answer, respond to that, Michael. I don't want to get into too many details here, but I can tell you that for the dry screw Cobra, the NC400, there is very little maintenance. However, we advise from daily visual inspections to check on the oil and the cooling liquid, as well as any type of leak. So this is just the visual. Now, depending on the application, you should check and clean maybe monthly the oil fill vent filter, as well as the pump inlet filter. We recommend about every 1,000 hours to drain the silencer, and every 5,000 hours drain and change the oil, as well as the cooling liquid. Every maybe 10,000 hours, and again, it all depends on your process. You can check the seals, and they could be replaced if necessary. But then every 4 years, an overhaul is recommended. Now, on the liquid ring, which is the Dolphin LT630, depends again on the application, but what we look at for the liquid ring, we check the noise and vibrations, check to see if there's any kind of leaks, check the operating temperature, liquid temperature, and then every 1,000 hours, maybe regrease the bearings. Again, check the inlet, and we do recommend an overhaul here every 5 years. So, but with service centers around the country as well as the world, any kind of repairs and overhauls can be scheduled quickly.
Okay, sounds good. And I have a question. It's kind of a bit of a background question for either of you. Someone is wondering, does Bush actually manufacture liquid ring vacuum pumps?
Yes, we do manufacture the liquid ring vacuum pumps. Our manufacturing company is either here in the U.S. as well as the U.K.
Okay, great. Our next question is, what is the coating on the dry screw pumps used for?
Sure, I'll go ahead and take that one. So the coatings that we use, so they create a dry lubricated film that goes on the surface. They do a couple things here. So it improves the protection that you kind of prevent the corrosion. It also has anti-friction properties. Now, they have really tight tolerances, so the coating actually never comes in contact with anything. And you can get away with non-compatible surfaces sometimes, actually, when you're using the dry screw if you have it in a vaporous state. But we've learned just from experience that having these coatings just makes it more reliable in the longer run. And you also have that options of coating as well, depending on the application, so you have different levels of protection there.
Okay, sounds good. And I'm realizing now that we actually have another question about your manufacturing capabilities. So Teodora, maybe you want to take this follow-up. Are you able to manufacture the dry screw pumps with ductile iron housings and stainless steel rotors?
So not at this time. So we do manufacture the pumps with the ductile iron for the screws. And the reason why we don't choose another material is because we keep everything in a gas state there. And what we use is the coating to prevent any kind of corrosion in the pump. So no, we do not.
Okay. And we do have a couple more questions that have come in. This is for either of you. Can a receiver function as a liquid separator to protect the dry running pumps from liquid slugs?
Sure, I'll go ahead and take that. So the simple answer is yes, potentially. So it depends. Part of what a separator might do when you have an inlet, when we call them the knockout pots, part of it is you have the tangential kind of flow. So essentially, if air comes in mixed with water, it's hard to go through the physics of coming out the top. So you could use a receiver to get rid of some of that. Now, I do want to be careful because in a knockout pot, you also have a filter potentially and a demister pad that can get some of those fine particles out. So A receiver wouldn't necessarily have that, and you could potentially have some water and trail to go through. But especially if we're just specifically talking about slugs, the tangential flow would most likely knock most of that out. Again, depending on your pressures, flow, and the size of the receiver and how that's designed.
Okay. We just have one more question left, so just a reminder to the audience, if you have a question that you'd like answered now's the time to submit it into the Ask a Question box. This is for either of you. What makes the overhauls complex for the dry screw vacuum pumps?
Well, we say that they're complex. We compare them with the liquid rings, where the overhauls on the dry screw tend to be a little bit more complex due to the recoating on the screws, and the tight clearance is needed into the dry screw pump. These, we tend to have them scheduled with our service centers, but we also have options for exchange pump in our fleet that could make the overhaul downtime a lot quicker. Another very important thing to keep in mind is that by having just a good regular maintenance, you could reduce the cost of any kind of repair or overhauls for these pumps.
Okay, great. Sounds good. And unfortunately, we have run out of time. Audience members, if there was a question that we were unable to get to, or if you think of a question later, you can always go to pharmamanufacturing.com and submit a question, and we will pass them along to our presenters. Any questions we were unable to get to because we've run out of time, we will also pass along to our presenters. Thank you, Michael and Theodore, so much for fielding all those great questions. Just a final reminder to everyone, please let us know your thoughts on this presentation by answering our brief survey, which will appear on your screen shortly. Your candid answers are appreciated, and they help us craft future events. And again, this webcast will be available at pharmamanufacturing.com. You can feel free to log in to view it any time or pass it along to coworkers. We also encourage you to visit pharmamanufacturing.com to gain even more access to tools and resources aimed at helping you achieve on-the-job success. And on behalf of Pharma Manufacturing Magazine and the folks at Bush Vacuum Solutions, thank you so much for your attendance and have a great day.
Thank you.